start the last session of the first day. First speaker in this session is Luca Maxia. He will talk about TMD set function and its application.
First of all, I'd like to thank the NISER for the invitation to provide this talk, in which I will discuss as this mentioned for series, and this work in collaboration with the board and Book something one. Indeed, actually, it should have been done by Board, but it's not here, so I take the lead for this reference. So this is the outline I would like to discuss. So basically, I will first of all introduce the TMD shape function in series. So and why it is needed for TMD factorization. We'll do it in a very simple way. Then I will focus on the main part of this talk, in which I would like to discuss how we achieve the perturbative tail of such object via matching procedure, in particular taking into account the pole structure of the hard amplitude that has been neglected in previous talk. And then I will move to the Q dependence that seems to appear in such objects, which suggests a process dependence. Finally, I will move quickly on the opportunities of the EIC to investigate such objects, giving some possible example and some idea. So first of all, as mentioned again by Christian, I'll give you an idea why quarkonia are interesting, in particular since the topic of this workshop. If you study processes that involve quarkonia, you are actually sensible to gluons. So if you want to investigate the gluon distribution of proton, for example, look at such processes like in hadron collision, you have proton-proton collision into quarkonia like eta C, chi C, double jet psi, can be interesting. Even in some extent, the single jet psi, with some caveat that I will not discuss here. But moving to EP, you have series, so EP into jet psi, but also you can have jet psi plus something else, like jet psi plus photon, as studied by Asmita for the asymmetry that can access the Bermudas, or jet psi plus jet, again studied by Asmita and Christian, for example. But here in this talk, I will focus on semi-inclusive deep analysis scattering. So just to give you the theoretical framework, this is the process I'm looking at. I leave it here so everyone can see all the kind of momenta. I will talk about that. In particular, I will do a very somehow simple discussion. So I will take only unpolarized objects in initial state. In particular, I take into account only the azimuthal angle of the final jet psi. So the differential cross-section is described in such a way. So you have a 4 structure function, 2 phi independent, FUT and FUL, and then you have 2 asymmetry, cos phi and cos 2 phi. In particular, since we are discussing about quarkonium production, we don't know precisely how to describe its formation, so you have to adopt several models, one of the models available. But in particular here, I will focus on the non-relativistic QCD, okay, which for jet psi can be thought as an extension of the color single model. So in the color single model, you produce the CC bar that form the jet psi at the perturbative level. And this CC bar is in a color single state. So basically, you are producing the jet psi at the perturbative level, in the hard amplitude. Instead, in the relativistic QCD, you also allow the production of corrupted states. So the CC bar can also be in a corrupted state, and then evolves by soft gluon emission into the final observed meson. Of course, this is not the full story. There can also be other models I mentioned here. For example, there is this improved color evaporation model, and also the fragmentation function. In particular, this last one can be connected to the relativistic QCD, because this fragmentation function has some rules that connects them to the long distance matrix element, okay, which are the non-perturbative parameter of the relativistic QCD effective field theory, which are universal in principle. Okay, now let me introduce the TMD shape function by a very simple analogy. So you are studying semi-inclusive deep analysis scattering. I call it like HADRON. So you are studying, for example, a pion in the final state, and the cross-section is described in such a way. So you have the hard amplitude, Then you have some non-perturbative part for the initial state, so the TMD, a PDF, for example, and then you have something for the final state, in particular a fragmentation function. If you move to quark-onion, then instead of the fragmentation function at the end, and in particular if you adopt an TVC-QCD, you will have the non-Lisa matrix element multiplied by this naive delta mass equivalence conservation. Now, if you move, so this is very for collinear, so high transverse momentum. If you move to the small pt limit, instead of the fragmentation function, you will have the TMD fragmentation function. So these objects will acquire some KT dependence. In the same way, also the non-Lisa matrix element has to be generalized. So they also have to acquire some KT dependence, and this quantity, so you will describe a new quantity, which is the TMD shape function, which was first introduced by these two papers, in particular the first one. And just to summarize, so they still encode the information about the evolution from the general state to the physical observed quarkonia, but also takes into account the exchange of gluons with other co-ordinate sources in particular. So I will focus mostly on that. So the idea now is to achieve some information of these new objects by a matching procedure. So I will look to the QT spectrum. QT is the transverse momentum of the virtual photon. Usually experimentally you look at the transverse momentum of the jet psi, of the observed particle, but the two are easily related. So we can discuss in one term or the other. In particular, as theorists, we prefer QT. So I will look to the spectrum, and you can identify two regions. That's pretty normal and well-known procedure. So you have a high QT, in particular higher than a typical lambda QCD, a typical QCD scale, let's say around 1 GeV. You apply collinear factorization. Whilst if you move to the small QT, so QT is smaller than the hard scale of your process, you will apply TMD factorization. And you see the two conditions are different. So in principle, there is an overlapping region. And if they are describing the same dynamics, they have to be matched. Okay, so they have to be the same. So by this simple sentence, I can get some information about the perturbative tail of the TMD contribution from the collinear one. So let's first of all discuss a little bit about the hard part of the two objects. So from the TMD point of view, I do again the lowest order, so the simplest case. So we produce a J psi at the lowest order is possible by the virtual photon gluon interaction. And you produce a CC bar. This is a purely co-octet object because you have a co-octet in initial state, so we'll have a co-octet also in the final state. And since it is a 2-to-1 process, everything is fixed. Okay, so all the variables are fixed. If you look to the cross-section, at the end of, from the 4 structure functions that you have at the beginning, only 3 of them survives. So we have the FUT, FUL, and the cos to phi asymmetry, where the first 2 involve the convolution between the amperized gluon TMD and the TMD shape function, while the latter involves the Burmulders and, again, the TMD shape function. So first of all, let me stress this point. That's why we need to investigate such objects, because indeed, if you want to extract information about the gluon distribution, that's, I would say, the most interesting point at the end, you need also to have some information about the TMD shape function. Otherwise, you are not doing the correct operation there. In particular here, I consider the possibility that here we have a different kind of TMD shape function that is convoluted between the amperized gluon TMD and the gluon Burmulders. So somehow, in some way, some equivalent of the Collins fragmentation function. But I will discuss a little bit more later. From the collinear point of view, instead, in this case, you need to produce the J psi a high transverse momentum, so you need some of the objects in the final state that compensate it. So the lowest order is the virtual photon parton fusion, and you have a CC bar and again the parton at the end. And the cross-section is the one I showed you a few slides ago. In particular, I will go a little bit into detail because it's important to stress a few points here. the partonic hard amplitude is evaluated in such a way. So you have again the lepton tensor and some hadronic tensor. In particular, here you have a delta, which is the main point of the next few slides. A delta that is based on the momentum conservation that is given by this formula. So it's very similar to the light hadron series again, but have also the inclusion of the mass. Okay, because yeah, you will see that there is some relation with, of course, since you have a heavy object, the jet size are heavy objects, you will have the mass appearing here and there. Okay, so the idea now is to, we have this kind of result, so you get this kind of result for the high tremendous momentum, you want to achieve this small QT limit, so you want to go into the intermediate region. So a schematic way to do that is that, so basically you start from these diagrams that are valid for the high tremendous momentum region, and you do the small QT limit. So basically what happens is that the contribution split up into terms. One of them is the 2-to-1 partonic process, so the same that applies to the TMD case. So there is actually a connection there, and this is combined with the soft gluon emission that has to be pressed in some way. And to operatively do this kind of operation, you need to expand the delta I just show you in the small QT limit. So if you do that, you will get three different contributions, one for the delta 1 minus x, another one for the delta 1 minus z, and then a double delta. But let me go a little bit about this detail because it will be important, in particular a key point in the next slide. So if you want to achieve this kind of result, I will not go in very much detail because if you want to do that, you can look to this paper. But the key point here is that, so you have this delta. To evaluate this small QT limit, you use two test functions for the two dependencies, and these test functions are continuous. Okay, so you need to have this continuous test function, and then you start to integrate over these variables. So for example, here I integrate over x, and I get this integral, and then to get the expansion, I split up this integral into three terms, okay, which are operation that is achieved by using this formula, okay? And if you evaluate the integral for these three terms, at the end, you will end up with the three different contributions of the delta as small qt. But again, I repeat myself, the key point here, you have continuous test function, okay? So the question now is that, are the structure function really continuous for all the kinematic region? Well, in principle, I can do this kind of operation. So this is a general notation for the structure function. So it can be either FUT, L, cos phi, cos 2 phi. Okay, it's general. And I can expand in terms of pole of this kind. So you have 1 minus z divided by 1 minus x prime. And this function here, FU0 and the FUK, for the different k order of these poles, are continuous. Okay, which means that for the first one, I can actually apply the delta, because that's a continuous function, so it's perfectly fine, it's well behaved. So in that case, I can apply the delta, I will have no problem. But if I have this kind of poles, in that case, although this function is continuous, I cannot apply it because I multiply by non-continuous function. So in that case, they have to be treated differently. So the question is, there are this kind of pole? And the answer is yes, they are. Not for all structure function. They are relevant only for the gluon channel, and in particular only for the FUT and FUL structure function. And they appear up to the second order. In particular, so what happens is that among the relevant part of the QT expansion, so which are these two terms, this kind of pole modifies the double delta, okay, because you can see it's actually a pole when you have both z and x equal to 1. So it modifies this kind of pole, so this coefficient is not correct for these cases, and it has to be modified in such a way. So you have half of the log, And when I talk about log, I intend the log of Qt. So I'm talking about the Qt dependence. So you have half of the log and some constant term, again, constant with respect to Qt. Okay, so there has to be modified. Another way to check if this kind of result is correct is thinking again that when you do this kind of operation, you have that your result is split up between the hard 2-to-1 process combined with a soft gluon emission. So you can actually evaluate this soft gluon emission by using the equal method. So you take the 2-to-1 amplitude, you attach soft gluons to your different corrupted objects. So you have the initial gluon and the two heavy quarks lines. And you take the squared amplitude, and then you integrate over the extra phase space that is produced by these extra soft gluon you are emitting. And okay. And of course, this transverse momentum of the soft gluon is fixed because it's given by the Qt. Oh, it disappeared, okay. And it's fixed because it's given by the transverse momentum of the psi of the virtual photon. So you have to integrate only over the minus or plus the direction, depending on your frame choice, among momentum conservation. So for momentum conservation, you have that the bottom of the integration is fixed by the presence of the transverse momentum, which is non-zero. So if you do this kind of integral, at the end, you will end up with basically the same result. Some proportional factor, which are not writing here, but yeah, it's the same result. So you have half of the log plus some constant. And since I have this picture, I make a very quick connection with the fragmentation function I mentioned at the beginning, because basically if you look to these two diagrams at the end, so you have a CC bar, okay, then you emit a soft gluon, and then you produce the J psi. So it's, in such a way, there's some kind of evolution of this quark per fragmentation function. And indeed, so basically this term of the function I showed you before when I showed you all the models, no, all, some of the models for the sky quark formation. So indeed, since these kind of objects are connected to the LDMEs, it makes sense that if you go in the KT limit of them, also those terms are somehow related to the TMD shape function. So the kind of evolution are somehow connected also to the TMD shape function. We didn't explore that, so that's just a suggestion that I firmly believe there is there. But yeah, I just leave for the audience as an hint for, yeah, whatever. But now, so we have checked, we have done all the calculation for the small Qt limit, and we can compare with the evolution of the TMD result. So we evolved the TMD result from small Qt to higher Qt to the intermediate region, and we check if we solely take the TMD PDF evolution, if that is enough to accommodate all the logs coming from the collinear. And we found the following results. So first of all, you see there is no cos phi, because indeed the cos phi is suppressed in the TMD region, and when you do the small Qt limit of the collinear, it's also suppressed, so it's not appearing here. If you look to the cos to phi instead, it is perfectly matching, so the two coincide in the intermediate region, which implies that we cannot say much about the perturbative tail of the TMD shape function when it's convoluted with the Bermulders, which doesn't mean it's not there. It doesn't mean that this is the full result. It only means that we need to go next order to observe it and check if it is actually the same or it can vary. Instead, if you look to the FUT and FUL cases, you have a mismatch. So if you take only the TMD evolution, it's not enough to accommodate all the logarithm that appears there, which implies that some of these logarithms need to go into the TMD shape function. So by allowing the TMD shape function to solve the mismatch somehow, you will have that the perturbative tail of these objects is given by this quantity. So it takes basically all the Qt independent terms. I've also to say that, again, I will stress this point, it is only the leading order result. So, and also we are considering up to certain order of the velocity expansion, which is the other parameter you have in RTB-CQCD. And up to this point, the bulk of the result is only core octave waves, in particular 1S0 and 3PJ in this kind of spectroscopic notation, okay? Doesn't mean that you don't have other contribution from other side. Okay, now I want to stress a little bit more about this point that if you look at this kind of result, you have the TMD shape function as a Q dependence, where Q is the virtuality of the photon, okay? So it is strange in principle that something that is quarkonium, Jepsi related, is inside is a dependence on the photon, okay? Which is, yeah, not directly connected. But one point we can thought at the beginning is the following, is that the previous equation is obtained by choosing a specific scale. So I choose a scale, a hard scale, to do the match. In particular is this one. So the idea is that, okay, and this is the same result, but in BT space, because it's more convenient for me for doing this kind of calculation, but it's the same. So you see here the same kind of result. So one can ask if it's the choice of the scale that produce this Q square. So you can somehow trace back, do maybe reverse engineering, whatever, to reintroduce back this general mu dependence, and you will find that, yeah, no, it's not the case. The Q is still there. Actually, it's somehow worse, because now we have this term squared. Okay, so it seems like there is some process dependence, which is somehow strange, but there is also some connection with other literature, because if you take the open quark, so instead of producing the Jepsi, so you have the bound state, you produce the open quark. In that case, you also find a soft factor that depends on Q square, okay? And just to see why this point is a little bit strange, let me do an analogy with the TMD PDF. So if I take again, the high scale, the evolution at highest hard scale of the TMD PDF, you will get some kind of result where Q now is some hard scale that depends on the process. And you can see that this matching coefficient have this dependence in it. So one can think, okay, yeah, it's the same kind of stuff. Not really, because again, here I have done evolution up to this scale. If I take the scale to be general, again, you will have that most of these Q dependence completely disappear. But there is still one, okay? Then you can say again, okay, yeah, it's the same stuff that you are showing before. So yeah, it's not process dependent, because the TMD PDF is not process dependence at this level. But it's different, again, because this Q square arises from the rapidity regulator, okay? And you don't have rapidity divergences related to the TMD shape function. So this kind of log is not present for the TMD shape function. It's not there. And this is kind of an argument in agreement with other papers already. So this kind of terms is not there. So you cannot motivate this quantity here as due to rapidity regulation. Okay, is there from process dependence at the end, in the bottom line. So since I repeat, it's strange that you have something that depends on the process for the evolution of the quarkonium, of the CC bar into the quarkonium. It is natural somehow to speed up this term. In particular, also because if you look again the open quark scenario, you will have that the soft factor can also acquire azimuthal dependence. Okay, this is shown by, for example, this talk here that I stole this picture from by Ferrara. You can also look this kind of paper from Catani and collaborators, where you have that the soft factor acquires azimuthal dependence. So it is maybe it's more natural that those kind of dependence arise also from this a process-dependent part of the TMD shape function. So the idea at the end is that the full result is split up in two terms, one that is universal and the other one which is process-dependent. And you can do that in several ways. From the Occam principle, we suggest this kind of separation when you have now this universal part that is Q independent. It depends only on the J psi mass and the Hart scale that you can choose. And then you have a process-dependent part that depends on Q square. And here I suggest a way to test that if this is actually the case. So the idea is the following. Suppose, for example, J psi production, you can think about two cases. So one case when you have two scales, like CDs I discussed now, and a case when you have a single scale, a single scale, like hadron collision, but it can be also other cases like photo production, it's okay. I mean, yeah, I took this as an example, but I mean only cases where you have a single scale. Because in such case, it is more natural that if you evaluate this object at this single Hart scale, this process-dependent term will be suppressed somehow. So in such case, it's easier to extract the universal part of the TMD shape function. Then you can evolve this term up to the scale you want to measure in the two Hart scale scenario, and combine with the process-dependent part that you evaluate there. And to test if it is actually correct, then you can evolve everything for a different scale again, for example, for upsilon production, and see if your calculation still works there. So again, I repeat, you go from one Hart scale, when you suppose that this process-dependent term is suppressed, then you extract the universal part, you combine with the process-dependent part of the two Hart scale, and to test it, you evolve to a different scale again, for example, upsilon production, okay? Now, to give you some idea, so I go to the last part of my talk, I give you some example. One idea, again, I discussed this kind of results, so the differential cross-section for the TMD case, and if I focus only on the FUT and FUS, so I'm talking about symmetries, already here you have some interplay with the TMD shape function. So here I just show you an indicative figure, don't take it too seriously, although yeah, it's well done, but don't take it too seriously, just to have something to talk with. So you have here in red the collinear part that diverges, and here in green you have the TMD, and here in blue you have some match curve that connects the two, and here in particular I use this inverse error weighting method described here in this paper. But the point is that, so if you have data from EIC, very precise data, you can have point here that goes down to the TMD region, and here you can finally extract the gluon TMDs, but not only, because up to in this talk, I only talk about the perturbative tail. So data here can extract also information about the non-perturbative content that we cannot know apart from making some model and extracting for data. And also another possibility that maybe can be done at the EIC due to the high luminosity and precision is that checking this match as a function also of Q. So checking for different Q. And I will go a little bit more on this point at the end. Another thing that we can look at is J psi polarization, okay? Polarization of the J psi. And again, since the Burr-Mullers starts at order alpha s, you need to have a next order calculation to get the perturbative tail of this TMD shape function. And just to have a conclusion for my talk, I give you this final example. So this figure is an analogous from this paper when they studied this lambda in terms as a function of Q square. It's not the exact same figure, but again, it's analogous. And they show this kind of results. So if you take the TMD factorization, okay, and you look to the lambda, you see that the result of this lambda vary depending on this ratio between the long distance matrix element for the P wave, the 3P0, and the long distance matrix element for the S wave. Okay, in particular, if the ratio is positive, like for this choice, you will have a negative lambda, while if it is negative, you have a positive lambda. But this is a very limited result, so although it looks like a very strong conclusion, it's actually not, in my opinion, very strong, because we are working only in the TMD factorization, which means that, again, all the variables are fixed. In particular, the J-psi elasticity is 1. Okay, so you are only looking to the single bin. And if you look to a more broad bin, so I show here the same kind of calculation, but integrating over Z, so moving a little bit away from the TMD region, you will see that the color single channel start to be very relevant. So while in this case, again, it's only color channel, so everything, color single channel is very suppressed, here it starts to be very relevant. And in particular, if you take those two curves and I compare with the previous one, here, dashed lines, you will see that, yeah, they're much closer to each other. So to actually conclude that you can have some such a sensibility, you can do some kind of extraction, you, first of all, again, you need some connection between the TMD and collinear region. And here, again, is respect to Q square.